Welcome to an introduction to combinatorics. The topics we will be covering are rules of sum and product, permutations, permutations with repeated symbols, permutations in nonlinear arrangements, combinations, the binomial theorem, and combinations with repetition. These last two topics may be in a second video. Definitely they will be covered in class. Our first topic, rules of sum and product. First, the rule of sum. I associate this with the word or because of this or in the definition. If a task can be performed in m ways, while a second task can be performed in n ways, and the two tasks cannot be performed simultaneously, then performing either the first or the second task can be performed in any of m plus n ways. The rule of product, which I associate with the word and, because you're going to be doing a first stage and a second stage. This is also known as the principle of choice. If a procedure can be broken down into a first and second stage, and there are n possible outcomes for the first stage, and if for each of these outcomes there are n possible outcomes for the second stage, then the total procedure can be carried out in the designated order in m times n ways. It's a very wordy definition, but we'll do a couple of examples which hopefully will be illuminating. So for our first example, we are going to look at a library that has 4 math books and 3 art books. Apparently, it's a very small library. Anyway, so our first question, how many ways can I choose either a math or an art book? And our second question, how many ways can I choose a math and an art book? So we'll do the first question first. How many ways can I choose either a math book or an art book? I wrote this out. We're going to choose a math book or choose an art book. And because we have the or here, that's going to tell us we're going to use the sum rule. So there are 4 ways, 4 ways to choose a math book. And then we have the sum rule, the or, and choosing an art book can occur in 3 ways. So we have 7 ways. The next question, how many ways can I choose a math and an art book? We will imagine this occurs in 2 stages. Our first stage, we are going to choose a math book. We're going to do a second stage, and we're doing both the first and second stage, so we'll be using the product rule. And then we're going to choose the art book. So again, 4 ways of choosing the math book and 3 ways of choosing an art book. So there are 12 ways. So for this last type of problem with the product rule, there's a really good diagram, a tree diagram, that really illustrates how those 12 ways come up. I will show you that in the next slide. So we're going to go look at our last example, and we're going to look at the tree diagram, kind of a visual tool for us. We're going to imagine, again, that this choosing the math book and the art book occurs in 2 stages. In stage 1, we're going to choose the math book. And in stage 2, we're going to choose the art book. So in stage 1, there are 4 math books to choose from. And we're going to title those books very unoriginally, Math 1, Math 2, Math 3, and Math 4. So for each of these outcomes, if we choose, for example, Math Book 1, then there are 3 art books in stage 2 that we can choose from. Art Book 1, Art Book 2, Art Book 3. We're going to get the same choices if we had chosen Math Book 2. Then there's Math Book 3. We can choose one of the 3 art books. And Math Book 4. So if you follow this tree diagram, you can see you have 12 different ways of choosing 4 math books and 3 art books. If you follow this branch of the diagram, you get Math Book 1 and Art Book 1. You follow the next branch, you get Math Book 1, Art Book 2. Math Book 1, Art Book 3. Math Book 2, Art Book 1, Math Book 2, Art Book 2, just kind of randomly choosing a path now. Math Book 3, Art Book 3, Math Book 4, Art Book 2, Math Book 4, Art Book 3. And then you can see over here all 12 possibilities. So the nice thing about this diagram is, one, it really does show you how you get the 12 possibilities with these branches. Two, and we'll see this later in the second lecture video, we talk about double counting, and this tree diagram, actually it's quite large, but you don't have to draw the whole tree diagram in order to get a sense of how double counting can occur. So in other words, you can get insights without even having to draw the entire tree. And then the last comment that I'm going to make is, this is a nice visual because you can see how in this very small library, remember I had commented there are only 4 math books and 3 art books, but you can see how once I wanted to show you this diagram, how it just exploded onto the page. And so what this should tell you, for example, if you're programming, you know, when you program at school, they give you an assignment. Usually it takes, 20 minutes maybe to run and complete at the most. Often it only takes 20 minutes at the most. Often it takes just a few minutes. But anyway, here you can see if you're going to do some sort of search algorithm, for example, through some sort of tree, maybe it's a tree showing different costs at different points in some project, or it could be a driving thing where you're going from one node to a next, or one city to a next, or any sort of search through many different nodes. Or for an example, when I did genetic algorithms, we were trying to parameterize our algorithm. Each parameter could take several different values, and then we were searching to see what was the best sort of set of parameter values to choose. And I had started an experiment where I was running it, trying out this genetic algorithm with different parameters, and I started, and at the end of the day it hadn't finished, so I came back the next day, it still hadn't finished. At the end of that day, it still hadn't finished, so then I thought, maybe I ought to do some calculations. And it turned out, we were running this program many times. There was just so many combinations of parameters that really it was going to take days, maybe even over a week or two. So we had to stop that, and we had to be a little more clever and narrow down our parameter list. So again, it's the idea that if you have these, where you're looking through many different combinations of things, many branches of the tree, you're really exploding things out, and in programming that can be an issue. Another example where we will use both the product and the sum rule. In an early version of BASIC, a variable name consisted of either a single letter or a single letter followed by a digit. How many variable names are possible? So again, I'm going to write out what we're going to do. We're going to choose a single letter, or we will choose a letter and a digit. So there are 26 ways of choosing a single letter. We have the or, so we're going to use the sum rule. Then we're going to choose a letter, and then because we have the and, we're going to use the product rule. And there are 10 ways of choosing a digit. So we have 26 plus 260, and then we have our final answer. Another example of sum and product rules, in particular the product rule. A board of directors has 4 members. How many slates of president, vice president, secretary, and treasurer can the board make? So I can think of this as a multi-staged process where in the first stage I choose the president, then I will choose the vice president, then I will choose the secretary, and last I will choose the treasurer. So again we have this the tree diagram where I start off choosing president and I have 4 people to choose from. My next stage I'm going to choose vice president. But now that I've taken one person away to be president, I only have 3 people left to be vice president. So you have this tree diagram. The third stage is choosing secretary, so I have 2 people. And then this diagram is going to get really cluttered, so we're going to go imagine we have the rest, and then we'll choose treasurer last. But by this time, there's only 1 person left. So as I said, our diagram's getting a little cluttered, so let's approach this a different way. Let's list out the steps we're going to do. First, we're going to choose our president. And our second step is choose vice president, and we're going to choose our secretary, and we're going to choose our treasurer. Don't even have room for that. So there are 4 people to choose from when I choose president. Because we have an and, we're going to use our product rule. Now there are 3 people left for vice president. Then once we've chosen president and vice president, there's only 2 people left to choose secretary. And then there's 1 person left as treasurer. So this is going to give us 24 ways that these 4 people can be arranged as president, vice president, secretary, and treasurer. And I did, just to point out, I did use the word the 4 people can be arranged as president, vice president, secretary, and treasurer. So now we've talked about the rules of sum and product. So our next topic will be permutations. So a permutation is any linear arrangement of a collection of n distinct objects. So the idea is that it's an arrangement where order matters. We'll start with linear arrangements and then later we'll do other circular arrangements. Also, we have n distinct objects. That'll be relaxed a little bit, but it is important to remember we're talking about arrangements of distinct objects. So we're going to look at permutations, and we're going to start with our last example with the president, vice president, secretary, treasurer example. So if you recall, we considered this a 4-stage process. The first stage we chose the president, then we chose the vice president, secretary, and treasurer. So the 4 stages, naturally, because you have these ordered stages, naturally implies some sort of order. So I could actually think of this as choosing a first person, a second person, a third person, and a fourth person. So in other words, instead of the role of president, I could say this is my first person. Instead of the role of vice president, I can assign that person the second person. Secretary, I could assign the role of third person. Treasurer, I could assign the role of fourth person. In other words, these 2 questions here, how many ways of making a slate of president, vice president, secretary, and treasurer, is the same question as how many ways can I arrange 4 people in a line. Again, instead of the roles of president, we're looking at the role of first person in line. Instead of vice president, second person in line, etc. More to the point, counting the number of permutations is a direct application of the product rule. Order is inherent in the product rule. This is because the product rule assumes a first stage, a second stage, a third stage, etc., and the order of those stages is important. Another permutation example, how many ways can I arrange 5 books? So I imagine a multi-stage process where first I choose a book to be the first book, and I'll choose a book to be the second book, and a book to be the third book, and a book to be the fourth book, and a book to be the 5th book. You can see I'm running out of space. So there are 5 books to choose from when I choose the one to place first. Then there are 4 books remaining to choose as my second book, 3 books, 2 books remaining, and finally I only have 1 book left. So I have 120 arrangements. Another example, how many different slates of president, vice president, secretary, and treasurer can be made from 10 people? Again, this is a process. We choose our president, and then we choose our vice president, and then secretary and treasurer. With 10 people, this can be done 10, and then 9, 8, and 7 ways. There is a permutation formula. If there are n distinct objects, and r is an integer greater than or equal to 1, but less than or equal to n, the number of permutations of size r from n objects is p of n r, that's the notation, is m factorial, it's a factorial, over n minus r factorial. A quick example of that from that formula. So if we have 10 people, we want to arrange 4 in a line. So in this case, n is equal to 10 because we have 10 people. R is our integer greater than 1 but less than 10, therefore. And again, we're choosing R, a permutation of size R. So in other words, we're going to arrange 4 people. So in this case, we have 10 people, but we're going to take 4 and arrange them in a line. So we have 10 factorial over 10 minus 4 factorial. And this is kind of a neat thing about factorial notation. We have 10 times 9 times 8 times 7 times 6 factorial. I don't have to write out the 6 times 5 times 4 because the bottom of my equation over here is equal to 6 factorial. Then I can cancel out my 6 factorials and I get the 10 times 9 times 8 times 7, which looks a lot like the solution I got in my last example. Okay, so we've covered rule of sum and product. We just covered permutations. So our next topic is permutations with repeated symbols. We're going to motivate permutations with repeated symbols with an example problem. How many ways can I arrange the letters A, L, L? So one common theme in mathematics is if you have a new type of problem that you may not know how to solve, you try to relate it to a problem that you do know how to solve. So the problem with the A, L, L is the two L's are identical, or they're repeated symbols. If we put little subscripts on the L's and made it A, L1, L2, we would know the answer to this question because then we would use our product rule, choose a first letter, a second letter, and a third letter, and we would see there are 6 ways to arrange A, L1, L2. So here I have written the 6 ways to arrange L1, A, L1, L2. But you might notice that I have paired them up. And the significance of this pairing is the only difference between each of the pairs is the arrangement and the letters, the L's, the L1 and L2. So in other words, if I took the subscript off, these two would be the same arrangement. Without the subscript, these two would be the same arrangement. And without the subscript, these two would be the same arrangement. So the way that these 6 ways, A, L1, L2 can be arranged is related to the arrangements of the letter A, L, L, is you want to divide your 6 ways by the number of ways you can arrange your L1 and L2. L1, L2. So you're going to divide 6 by 2 factorial, or just 6 divided by 2, which is equal to 3 arrangements, which you have here. There's the 1, 2, and 3 arrangements. There is a general formula for permutations with repeated symbols. If there are n objects with n1 of a first type, n2 of a second type, etc., on down to nr of an rth type, and n is equal to n1 plus n2 all the way to nr, then there are n factorial divided by n1 factorial and 2 factorial times all the way down to nr factorial. So just using our last example, when we have the letters A, L, L, so in this case, we have 3 objects, so n is equal to 3. Our A is our first type, so n1 is equal to 1 because there's 1A. Our L is our second type, so n2 is equal to 2 because there are 2 L's. So here we have our n is equal to n1 plus n2, just like this requirement here. And then our formula would tell us there are n factorial divided by 1 factorial times 2 factorial, which is equal to 6 divided by 2, which is equal to 3, which is what we got in our last example. One last note, I always like to write all the n types even when it's equal to 1, just because later I can see that these numbers should add up to the n on top. So we've done rules of sum and product, we've done permutations, We just finished repeated symbols, so our next topic is nonlinear arrangements. For nonlinear arrangements, again, we're going to use an example. If 6 people designated A, B, C, D, E, and F are seated at a round table, how many different circular arrangements are possible? So here I have my round table, and I'm going to imagine that at the top I have a seat, and I'm just going to assign someone to it. I have 6 ways of doing that. Then I'm going to assign someone to the next seat. I'll have 5, 4, 3, 2, and then I have 1 seat left for my last person. So the trick to circular arrangements is usually you'd want to think of, if we rotate the table, that these two arrangements are equivalent. Even though person A now has moved seats, they're still relatively in the same seated position because A is always on this side of B, who is next to C, who's next to D, who's next to E, and who's next to F. So these two arrangements are considered equivalent in circular arrangements. So to complete this problem, the first thing we did is we assigned someone to the first seat. There were 6 people. Let me erase that. 6 people to choose from. Then we assigned the second seat. There are 5 people left. And we went down until we finally assigned all 6 seats. But now we want to take into account all the different rotations. Well, since there are 6 seats, there are going to be 6 rotations. You can see them here. In this first configuration, A is in this first seat. But then you can see A can rotate to the second seat, to the third seat, to the fourth seat, to the fifth seat, and then back up. So there are 6 possible seats that A can take, and then the other people having the fixed arrangement will stay. So there are 6 rotations. So the final solution will be 5 factorial. So now that we've covered nonlinear arrangements, our last topic for this video is combinations. Combinations, and the words that you associate with combinations is from N choose R. Again, an example, how many ways can I choose 4 people from 10? In other words, from 10 people, choose 4, from N choose R. I specifically chose this example to be similar to our last permutations example where we had 10 people and we wanted to arrange 4 people. So we're going to do the thing in mathematics where we have a new type of problem that we don't know how to solve. We're going to try to relate it to a problem we have solved. And I'm going to give a little bit away by saying that this will work because commutations and permutations are related. Our last permutation problem was from 10 people we wanted to arrange 4 people in a line, and we did this by doing 4 stages. The first stage we chose our first person, then we had 9 people left to choose our second person, 8, and then 7 people to choose our fourth person. So this is our P of 10, 4. How does this relate to combinatorics? Well, I could have considered this problem as a 2-stage process, where the first stage I choose from the 10 people, I choose 4, and the second stage I arrange those 4 people. I've written those 2 stages here, choose 4 people from 10 and arrange the 4. So choosing the 4 people from 10, well, that's going to be my C of 10, 4. That's my choosing problem. I have the and, so I'm going to multiply, and the number of ways to arrange 4 people is 4 factorial. Equating these 2 sides of the equation, I get C of 10, 4, the number of ways of choosing 4 people from 10, is equal to P of 10, 4, divided by 4 factorial. Written in a more general form, C of nr, also I have this notation, n choose r, is equal to P of nr divided by r factorial. And you can see that combinations and permutations are related. So the general formula for combinations is C of nr is equal to P of nr divided by r factorial, where C of nr is the number of combinations, and that should be a parentheses, but it turned out to be a 9, or selections of size r from a collection of n distinct objects. And again, in this formula, you can see how permutations and combinations are related. An example of the combinatorics, the combinations formula, is how many ways can I choose a 5-person team from 12? So in this case, we're looking at C of 12. From 12, we're choosing 5. That's going to equal to P of n r divided by r factorial, where P of n r, and I reminded you of the formula here, is equal to n factorial, so that's going to be 12 factorial divided by n minus r factorial, and then of course I still need my, I'm going to take this 5 and move it down here. Okay, and another really easy way to do this, the notation that I often use for C of 12, 5 would look like this, 12, 5. So there's no division sign, but this is basically from 12, choose 5. And that's equal to 12 factorial divided by 5 factorial. So you get the 12 factorial, you just put it here. The 5 factorial, you put it here. And then the rest of the bottom is just your 12 minus 5. So that'll be 7 factorial. And so that these two numbers here should add up to the top number. Now that we've covered combinations, we've covered all the material for this video. Binomial theorem and combinations with repetition will be covered in a subsequent video and also in class. Do take some time to review these concepts. They are not too difficult when presented on their own, but when you start mixing all the permutations, the repeated symbols, the nonlinear arrangements, combinations, and then later combinations with repetition, it's very important that each idea is very clear. Thank you, and I'll see you in class.